Welcome to this problem walkthrough. Today, we'll explore problem number 699, titled Falling Squares. In this problem, we'll analyze how squares fall on a plane and calculate the maximum heights as they stack. Stay tuned as we dive into the problem and discuss potential solutions. In this problem, we are working with a series of 2D squares that drop one by one onto a horizontal number line. Each square is described by a 2D array called positions, where every element is a pair, left, side underscore length. The left value tells us where the left edge of the square is positioned on the number line, and side underscore length gives us the length of the square's sides. When a square falls, it lands on top of the tallest square it overlaps or touches. If it doesn't overlap with any other square, it simply lands on the ground. As each square falls, we need to calculate the new maximum height of the stack formed so far. Our task is to return an array ANS of size n, where each element represents the maximum height of the stack after the corresponding square has fallen. Let's go over an example to better understand how the squares fall and how the output is calculated. Consider the input positions equals 1, 2, 2, 3, 6, 1. The first square drops at position 1 with a side length of 2. Since there's nothing beneath it, it lands on the ground, and the height of the stack is now 2. So, the first value in our result is 2. Next, the second square drops at position 2 with a side length of 3. This square overlaps with the first one, and it lands on top of it. The new height of the stack is now 5, which is the height of the first square plus the height of the second square. At this point, the result array is ANS equals 2, 5. Now, the third square drops at position 6 with a side length of 1. This square does not overlap with any of the previous squares, so it lands directly on the ground. Since the stack height remains unchanged at 5, the final result is ANS equals 2, 5, 5. Let's consider another example. If the input is positions equals 100, 100, 200, 100, the first square drops at position 100 with a side length of 100. Since there are no other squares, it lands on the ground, and the height of the stack is 100. The second square then drops at position 200 with a side length of 100. It does not overlap with the first square, so it also lands on the ground. The maximum stack height remains 100, and the result is ANS equals 100, 100. Let's now review some constraints and edge cases for this problem. First, the number of squares, positions.length, can range from 1 to 1000. The left value of each square can go up to 10⁻8, and the side underscore length can be as large as 10⁻6. We also need to consider edge cases. For example, if there's only one square, the result is simply its side length. If the left values are very large, the solution must handle these efficiently to avoid overflow. For squares that do not touch or overlap with others, they should land directly on the ground. Finally, if a square overlaps multiple previous squares, it should land on the tallest stack it intersects with. These considerations are critical for building a robust solution. To solve the falling squares problem, we can start by simulating the stacking process using a brute force approach. The idea here is straightforward. For each square that falls, we check all previously placed squares to determine where it overlaps. Once we identify the overlap, we calculate the maximum height the new square can reach by adding its side length to the tallest square it intersects with. This ensures that every square is placed at the correct height while also updating the overall maximum height recorded so far. Although this method is intuitive and simple to implement, it has significant limitations. The time complexity is n squared, because, for every square, we must iterate through all preceding squares to check for overlaps. This makes it inefficient for larger inputs. Additionally, it requires n space to store the heights of all the squares. While this approach is helpful for understanding the problem, it's not ideal for scenarios with many squares due to its performance bottlenecks. To address this, we explore optimized techniques such as the segment tree approach next. The segment tree approach offers a more efficient solution by leveraging a data structure that allows us to quickly query and update interval heights. Instead of iterating over all previous squares, we use the segment tree to maintain the maximum heights of specific intervals. The process begins by compressing the coordinates, which maps the potentially large number line into a smaller range, making it manageable for the segment tree. Once the coordinates are compressed, we can efficiently query the maximum height in the range where a square falls and update the segment tree with the new height after placing the square. This method reduces the time complexity to O n log n, as querying and updating the segment tree each take O log n operations. The space complexity remains O n due to the storage requirements of the segment tree. While this approach is highly efficient for large inputs, it introduces complexity in terms of implementation and debugging. For those looking for a simpler yet still efficient solution, the sweepline approach with coordinate compression is another viable option. Ultimately, the sweepline method with coordinate compression stands out as the most practical and efficient approach for this problem. It simplifies the process while maintaining the same O n log n time complexity as the segment tree approach. By compressing the coordinates, we reduce the problem size without losing any precision. This allows us to use a simple array to track the maximum heights at each compressed interval. For each square, we can quickly determine its maximum height, update the relevant intervals, and record the overall maximum height. The key insight here is recognizing that the problem boils down to efficiently managing maximum heights over specific intervals, and coordinate compression makes this manageable. This approach strikes a balance between performance and simplicity, making it easier to implement and debug compared to a segment tree. While it may not be as fast as brute force for very small inputs, its scalability and practicality make it the preferred choice for competitive programming and real-world applications. It handles overlapping and non-overlapping intervals seamlessly, ensuring both efficiency and flexibility in solving the problem. The problem involves stacking squares on a horizontal plane. Each square is defined by two boundaries, the left boundary and the right boundary. When a square is placed, it can either start a new stack on the ground or rest on top of an existing stack, depending on whether it overlaps with previously placed squares. Our goal is to figure out the total height reached by each square as we add them sequentially. To solve this, we begin by representing the squares as intervals, where each square is described by its left and right boundaries, L_I, R_I. These intervals are stored in a list, in the same order as the placement sequence. Next, we iterate through the list of squares. The first square always starts at height 1 because it forms the base. For every subsequent square, we carefully examine its position relative to all previously placed squares to determine its height based on potential overlaps. To determine where each square can be placed, we first check for overlaps between the new square and all previously placed squares. Overlap occurs if the intervals of the new square, L_new, R_new, and a previously placed square, L_prev, R_prev, satisfy the condition L_new R_prev and R_new L_prev. If overlap is detected, we then calculate the height of the new square based on the stacks it overlaps with. Specifically, we find the maximum height among all overlapping squares and set the new square's height to max_height plus 1, where max_height is the tallest stack among those overlaps. If no overlap is found, the square starts a new stack at height 1. After calculating the height, we record it in a result list to keep track of the heights for each square. This process is repeated for every square in the list. Once all squares are processed, the output is the list of heights in the order the squares were placed. The key to this algorithm lies in accurately detecting overlaps and propagating heights. Overlap detection ensures that the stacking respects the physical boundaries of the squares. By keeping track of the maximum height among overlapping squares, we ensure that each square is placed at the correct height, accounting for existing stacks. However, the straightforward approach of checking overlaps for each square against all previous squares results in a time complexity of O n squared, as we iterate through all pairs of squares. To optimize this, we can consider advanced data structures like segment trees or binary index trees. These structures allow us to efficiently query and update overlapping intervals, potentially reducing the time complexity of the algorithm. In terms of data structures, we use two main components: a list of intervals to store the boundaries of each square, and a height list to maintain the computed height of each square for quick access during calculations. When solving this problem, it's important to account for several edge cases. If no squares overlap, each square simply starts a new stack, and the heights remain at 1 for all squares. In the case of complete overlap, where all squares share some common region, the height increases sequentially from 1 to the total number of squares, as each new square is placed directly on top of the previous stack. A more complex scenario arises with partial overlap, where some squares overlap while others do not. This requires careful propagation of heights to ensure the correct stacking. Another subtle case involves nested squares, where one square is entirely enclosed within the boundaries of another. In this situation, the smaller square must be placed on top of the stack formed by the larger square. Finally, analyzing the algorithm's complexity, the time complexity is O(n) squared, due to the nested iteration for overlap checks, while the space complexity is O(n), to store the heights in intervals. While the basic approach is straightforward, optimizations can significantly reduce the time cost for large inputs. This Python implementation solves the falling squares problem, where we are tasked with simulating the placement of squares on a 1D plane and calculating the resulting heights. Let's break down the solution step by step. 1. Initialization. We start by initializing two lists, intervals to store the intervals of placed squares along with their heights, and heights to keep track of the maximum height at each step. 2. Iterating through positions. For each square defined by its left position and size, we calculate its right boundary as left plus size. The goal is to determine the height at which the square will be placed. 3. Finding maximum overlap height. We iterate through all previously placed intervals. If the current square overlaps with an existing interval, i.e., it does not fall entirely to the left or right, we update max_height to the highest point of overlap. For calculating new height, once the maximum height is determined, the new square's height is simply max_height plus size. We then append this new interval, with its height, to the intervals list. 5. Updating heights. The maximum height at each step is either the new square's height or the previous maximum height. This ensures we track the tallest height reached so far. 6. Returning the result. Finally, we return the heights list, which contains the maximum height after each square is placed. This approach ensures that the solution handles overlaps correctly and efficiently calculates the resulting heights. The time complexity is O(n) squared, in the worst case, where n is the number of squares, as each square checks for overlaps with all previously placed squares. This is sufficient for the problem's constraints and provides a clear and concise solution. Here, we start the implementation of the falling squares problem in Java. First, we import the necessary libraries and define the solution class. Inside the class, we have a method called falling squares, which takes a 2D array of positions as input and returns a list of integers representing the maximum heights after each square falls. We initialize two lists, intervals, to store the range and height of each square, and heights, to store the maximum heights at each step. Next, we iterate through the input positions array. For each square, we extract its left coordinate and size, calculate the right coordinate, and initialize max height to 0. The max height variable will help us determine the maximum height this square will rest upon. To calculate this, we loop through the existing intervals to check for overlap. If there is an overlap, meaning the current square intersects with a previous one, we update max height to be the greater of its current value or the height of the overlapping square. This ensures that we account for all possible overlaps when placing the square. Finally, we calculate the new height of the square by adding its size to max height, and we add this new square as an interval with its left, right, and height values. Once we have calculated the new interval for the current square, we update the heights list to track the maximum height so far. If the heights list is empty, we simply add the current height as the first value. Otherwise, we compare the current height with the last value in the heights list and append the greater of the two. This ensures that the heights list always reflects the maximum height at each step as we process the squares. Finally, we return the heights list as the result, which contains the maximum heights observed after each square has fallen. This completes the implementation of the falling squares problem. The use of intervals to track overlapping squares and the dynamic update of the heights list ensures an efficient and accurate solution. Here, we are solving the problem with an example where no squares overlap. The input positions are given as 1, 2, 4, 3. Initially, we have empty lists for intervals and heights. When placing the first square, its left position is 1, and its size is 2. From this, we calculate the right edge as 3. Since there are no existing intervals, the maximum height beneath the square is 0. Adding the square's size gives us a current height of 2. We then store the interval 1, 3, 2, and update the heights to 2. For the second square, its left position is 4, and its size is 3, so the right edge becomes 7. There's no overlap with the existing interval, 1, 3, 2, so again, the maximum height is 0. Adding the size results in a current height of 3. We store this interval as 4, 7, 3, and update the heights to 2, 3. The final output is 2, 3, representing the cumulative maximum heights after each square falls. Now, let's consider an example where the squares overlap. The input positions are 1, 2, 2, 3. Initially, the intervals and heights lists are empty. For the first square, its left position is 1, and its size is 2, so the right edge becomes 3. Since there are no existing intervals, the maximum height is 0. Adding the square's size gives a current height of 2. We store 1, 3, 2 as the interval and update heights to 2. For the second square, its left position is 2, and its size is 3, making the right edge 5. This square overlaps with the existing interval 1, 3, 2. To determine the maximum height beneath this square, we use the height of the overlapping interval, which is 2. Adding the size gives a current height of 5. We store the interval 2, 5, 5 and update heights to 2, 5. The final output, 2, 5, reflects the maximum heights after each square falls. Next, we examine an example with multiple overlaps. The input positions are 1, 2, 2, 3, 6, 1. Initially, both intervals and heights are empty. For the first square, with a left position of 1 and size 2, the right edge becomes 3. With no existing intervals, the maximum height is 0, and adding the size gives a current height of 2. We store 1, 3, 2 in intervals and update heights to 2. The second square, starting at left equals 2 with size equals 3, has a right edge of 5. It overlaps with the interval 1, 3, 2, whose height is 2. Using this as the maximum height, we calculate the current height as 2 plus 3 is equal to 5. The interval 2, 5, 5 is added to intervals, and heights are updated to 2, 5. Finally, the third square starts at left equals 6 with size equals 1, giving a right edge of 7. This square does not overlap with any existing intervals, so the maximum height is 0. Adding the size results in a current height of 1. We then store the interval 6, 7, 1 and update the heights list to 2, 5, 5. This means the third square's height does not affect the maximum height from the previous squares. The final output is 2, 5, 5, showing that after each square falls, the maximum heights are 2, 5, and finally 5. This concludes the example with multiple overlaps, where the solution handles intervals dynamically to calculate the correct heights at each step. To analyze the time complexity, let's break down the operations in the falling squares function. First, we have the outer loop that iterates over each square in the positions list. If the number of positions is represented by n, this loop runs n times, contributing n to the total complexity. Then, for each square, there's an inner loop that goes through the intervals list to determine the maximum height of overlapping intervals. In the worst case, when processing the ith square, there are I intervals to check, leading to a sum of iterations equal to 1 plus 2 plus 3 and so on, up to n. This summation simplifies to n asterisk, n plus 1, slash 2, which is proportional to n squared. Finally, appending to the intervals and heights lists happens in constant time per iteration, and since there are n iterations, this contributes an additional n. However, this is dominated by the nested loop, leading to an overall time complexity of n squared. Now, combining all the contributions we discussed, the time complexity is dominated by the nested loop, which results in n squared in the worst case. Shifting our focus to space complexity, the primary contributors are the intervals and heights lists. The intervals list stores tuples of the form left, right, current underscore height for each square. In the worst case, all n squares are stored, and since each tuple occupies constant space, the total space requirement for intervals is n. Similarly, the heights list stores one height value for each square, adding another n to the space complexity. Lastly, the algorithm doesn't use any additional auxiliary data structures, so the overall space complexity is determined solely by these two lists, resulting in n. The overall space complexity, therefore, is O(n), as it scales linearly with the input size. When comparing this brute force solution to optimized approaches, we observe a significant difference in efficiency. The current solution checks for overlaps by iterating over all previous intervals, which results in O(n²) time complexity. While this is straightforward to implement, it's not the most efficient. More advanced techniques, like segment trees or binary index trees, can reduce the time complexity to O(n log n by allowing efficient querying and updating of overlapping intervals. These structures avoid the need for a nested loop and are better suited for handling larger inputs. Finally, let's consider the different scenarios for time complexity. In the best case, all squares fall far apart from one another, meaning there's no overlap. Here, the inner loop executes only once per square, resulting in O(n) time complexity. In the average case, a square overlaps with a fraction of the previous intervals, leading to a total complexity closer to O(n²). The worst case occurs when every square overlaps with all the previous ones, requiring the maximum number of iterations in the inner loop and resulting in O(n² complexity. The proof of this quadratic growth lies in the nested loop structure, where the total operation scale is the summation of the first n integers, which simplifies to O(n²). Since no optimizations are applied, the space complexity remains O(n) due to the storage of the intervals and heights lists. When tackling the falling squares problem, there are a few common mistakes to watch out for. First, relying solely on a brute force approach can be problematic. While brute force might work for small input sizes, its O(n²) or worse complexity makes it infeasible for larger datasets, especially during coding interviews where efficiency is key. Next, overlooking edge cases is another frequent error. For example, failing to account for empty inputs, single-element inputs, or datasets with duplicate values can lead to incorrect results. Imagine a scenario where all the input squares are of the same size or there's no valid solution. These are critical to handle. Another pitfall is making incorrect assumptions about the input order. If the problem doesn't explicitly state that the input is sorted, assuming so can lead to flawed logic or unnecessary preprocessing. Finally, overcomplicating your solution can also hurt performance. For instance, adding steps like sorting or introducing extra data structures when they aren't needed can increase both time and space complexity unnecessarily. Another common mistake is not testing your solution for performance on upper bound constraints. This can give the false impression that your solution is correct, but it may fail or time out when applied to larger datasets. Now, in interviews, there are a few key strategies to keep in mind. Recognizing patterns is extremely valuable. For instance, many problems can be reduced to familiar techniques like sliding windows, dynamic programming, or binary search. Spotting these patterns early can save a lot of time. It's also important to approach problem solving in a structured way. Start by discussing the brute force solution and its trade-offs, then demonstrate your optimized approach. This shows clear and logical thinking. Communication is another critical skill. Be sure to explain how your solution handles edge cases, as this demonstrates thoroughness. Additionally, you can start with a simpler solution to ensure correctness, then incrementally optimize it. For example, you might begin with an O(n² approach and refine it to O(n log n) or O(n). Lastly, discussing test cases out loud during the interview helps the interviewer see your thought process and ensures you've considered all scenarios. Falling squares shares similarities with several related problems, which can provide useful insights. For instance, LeetCode 300, the longest increasing subsequence, is a classic dynamic programming problem focused on sequences. Similarly, LeetCode 354, Russian doll envelopes, combines sorting with dynamic programming to solve a nesting problem. Another useful comparison is LeetCode 1143, the longest common subsequence, which is foundational for sequence alignment and dynamic programming. And LeetCode 128, the longest consecutive sequence, uses hashing techniques to achieve O(n) complexity. Exploring these problems can deepen your understanding of patterns and techniques that apply to falling squares. Now, let's talk about alternative approaches. Dynamic programming is a powerful strategy here, as it allows you to break the problem into overlapping subproblems, solving each one only once and storing the results. While this approach can significantly reduce time complexity, it often requires more space. Alternatively, greedy algorithms can be useful for making locally optimal choices at each step, which may lead to a globally optimal solution. However, greedy methods aren't always suitable for problems that require global optimization, so their application depends on the specific scenario. Another approach worth considering is binary search, which is particularly useful in problems where you need to identify a specific threshold, such as the maximum or minimum value that satisfies a given condition. By leveraging the monotonic properties of the problem, binary search can significantly reduce complexity. However, it's important to ensure that the problem adheres to these properties for the method to be applicable. Understanding when and how to use these techniques, dynamic programming, greedy algorithms, and binary search, gives you a versatile toolkit to solve a wide range of variations on the falling squares problem and similar challenges. Great job! We've covered the falling squares problem, breaking it down step by step. Remember, this is a fantastic problem to practice simulations and improve problem-solving skills. Thank you for watching, and make sure to subscribe for more insights and solutions. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!